Hello friends, Mr. Burrell here. We're nearing the end of Unit 6. I know it's a bittersweet farewell. But in Unit 6 we've talked about graphing rational functions. We've talked about finding all sorts of different parts of the graphs of these rational functions, the holes in these functions, the asymptotes, the x-intercepts, the y-intercepts. All these different parts of graphs we've been able to find, and we've been able to draw what those graphs would approximately look like on a graph. So today, in 6.4, what we're going to talk about end behavior. This should be at the top here, probably. But we're going to talk about end behavior. This is the one part of rational graphs that we haven't quite covered yet. We're going to talk about end behavior of rational functions. And we're also going to talk about some real-world applications of rational functions. We're going to take a look at some actual real-world rational equations, some situations that can be modeled with rational equations, and how we would go about solving a problem like that. So this is what to kind of expect in this unit. By the end of this lesson, these are the things you're going to be able to do. You're going to be able to identify the end behavior of a rational function. We'll talk about what that means. You'll be able to identify a function's behavior at an asymptote. And you'll be able to solve a real-world problem with rational functions. Okay, let's dive in. So remind yourself, I guess, what end behavior is. We've talked about end behavior when it comes to polynomial functions in the past, but remind yourself, what does end behavior mean? When I say end behavior, what am I concerned with? Well, the end behavior, when I'm talking about the end behavior of a function, I'm trying to ask myself, how does the graph behave, or what does the graph do as x gets really big or really small? That's what we've been exposed to as it pertains to end behavior in the past. So I've had, I'll have like a graph like this or something, and I said as x goes to infinity, or as x goes to the right forever and ever and ever, what way does the function point, or where is the function going? And in this case, f of x was going to infinity because it's going up forever and ever and ever. In the other direction, as x went to negative infinity, or to the left forever and ever and ever, f of x, or y, was going to negative infinity because it was going down forever and ever and ever and ever. So that's what end behavior means. As the graph, as I'm going forever to the right or forever to the left, what's happening to the graph? Where is it going? What is it doing? So that's what I'm talking about with end behavior. So let's see if I can move my face out of the way a little bit more. So there are three ways the end behavior of a rational function can move. So, for example, if I have x as x goes to infinity, or as I'm going all the way to the right of the graph, or as I go as x goes to negative infinity, as I go all the way to the left of the graph, there are three different ways the end behavior of the rational function can move, or three different ways it can look, if that makes sense. So as x goes to infinity, y could move up. The graph could be pointing up. So that would look something like this. If I had a function like this that pointed, as I went to the right, it was going up forever and ever and ever. That might be what it would look like. So I'd write, as x approaches infinity, f of x approaches infinity. So if as x gets really big, y gets really big, this is what the end behavior would look like. As x goes to infinity, f of x goes to infinity. I'm going to skip down here to the bottom. Another way that the end behavior could look is it could be pointing down. So say I have a function like this. As I go to the right, it goes down, down, down forever. As I go to the right, it goes down. And I'm not doing the left sides of these graphs, but the same would apply to the left. If I was going to the left and the graph was pointing down, it would behave the same way. So in this case, as x goes to infinity, f of x goes to negative infinity because it's pointing down. It's just going to keep going down forever and ever and ever. This is what we're most likely used to from when we talked about polynomial functions. So there's another option that's going to present itself with these rational functions. Another potential way that the end behavior of my rational function will look is it might look flat. So say I have like a horizontal asymptote here, my rational function could look like this. As x goes all the way to infinity, the function doesn't point up or down, it kind of flattens out at one particular y value. So in this case, as x goes to infinity, f of x is going to approach or get closer to one specific number. As x gets really, really big, or as I travel this direction, y is not going to be going up or down. It's going to settle in right on one specific number, specifically where this asymptote is. So that's the third option for what the end behavior of these rational functions might look like. Okay, so let's look at some examples. So let's take a look. Which part of the graph do you look at to see where it moves? What location do you need for x? So if I'm given the question, what happens as x approaches infinity, I'm looking to the farthest right side of the graph. So again, if I have a graph, if I'm looking for as x approaches infinity, I'm looking as x goes to the right, the farthest right side of the graph, what is happening? What is going on? So what I write is wherever the y values are headed. So if I look at my previous chart, if I'm asked what happens as x approaches infinity, f of x could be going to infinity, f of x could be going to negative infinity, or f of x could be going to a particular number. It could be approaching just one specific number. So that's an option. If I was given the prompt x approaches negative infinity, on my graph here, I'm looking at what happens as I go to the farthest left side of the graph, because in the x direction, negative infinity is to the farthest left point of the graph. And what I would write, again, I refer to the chart up above, I'd either write f of x approaches infinity, f of x approaches negative infinity, or f of x will be approaching one specific particular number. We're going to see what that looks like in a minute here. So another option of what I might be asked to find is as x approaches a certain number. So if I'm looking not as x gets really big or really small, just as x approaches a specific number, I'm going to find that number on the x-axis, and on that, at that number on the x-axis, if there is a vertical asymptote or a hole, I'm going to look at both sides of that vertical asymptote or both sides of that hole. I'm going to ask myself, where are the y values headed on both sides of that hole or vertical asymptote? So say I have a vertical asymptote, and say I have a graph that looks something like this. Say this was at x equals 2. As x approaches 2, you'll notice that my graph on this side is pointing way up, and my graph on this side is pointing way down. So f of x would either be approaching infinity, going up, or negative infinity, going down. What we're going to see more often is I'm going to have a graph. Say I have a graph with a hole right here. I might ask you, as x approaches 1, 2, say 3. As x approaches 3, where are my y values headed? Well, maybe my y value right here is 1. So as x goes to 3, f of x, or y, would be getting really close to 1. Because at x equals 3 on both sides of this hole, I'm getting really close to the y value of 1. Okay? So that's what you would do if you're given this prompt, is x approaches a specific number. And the last thing I might ask you on some of these problems is find f of a number. So if I'm given a function, if I give you like a function, f of x equals x plus 1 over x plus 2, or something like that. Whoops, sorry. If I'm giving you something like this, I want you to find the point. So whatever that number is, I want you to find the x value of that point. If the x value of that point matches up with a hole, then f of x, or f of that number, the function value at that x point, is going to be undefined because there's a hole there. So if there's a hole at this point right here, you're going to write that point does not exist. That's what DNE stands for. Or you could write undefined or something like that. That point does not exist. So is there a value at the hole? If not, then you put does not exist, or undefined, or no solution, or something like that. So these are the different kinds of problems we might see. So let me show you an example of what a homework problem or a test problem might look like. So right here I have identify the following. So I have this graph. You'll notice I have a horizontal asymptote through y equals 1. I have a vertical asymptote at x equals 2. I have a hole right here at x equals 3. And you can kind of see what's happening on either end of my graph as x gets really big, as x gets really small, etc., etc. So as x goes to infinity, so as x goes to the right, what is happening to f of x? Or what y values are the graph getting close to? So you notice I'm going down, down, down. I'm kind of leveling out. I'm going to get really close to this horizontal asymptote. I'm never actually going to touch it, but it's going to get really close to the y value of 1. So as this graph comes down, it's getting really close to the y value of 1. So as x goes to infinity, f of x is going to get really close to 1. Because that's the y value here that I'm getting really close to. In the other direction, as x goes towards negative infinity, or as x goes to the left, what's happening to my graph? Notice what's happening. I'm going to keep going and going and going. I'm not going up or down. I'm just kind of flattening out, getting really close to this asymptote at y equals 1. So as x approaches negative infinity, f of x approaches 1. Same thing. It's getting really close to 1. It's never actually going to touch 1, but it's going to get really close. Here, this next problem says, as x approaches 3, as x gets close to 3. So, I'm not going to the left or to the right. I'm looking just here at x equals 3. So if I'm traveling on this graph, as I get really close to this hole, notice I'm approaching the y value of 2. Coming from this side, as I get really close to this hole, I'm approaching the y value of 2. I get really close. I never actually touch 2 because there's a hole there, but that's what this little arrow means, is I approach, I get really close to the y value of 2. So as x goes to 3, f of x gets really close to 2. So as x gets close to 3, y gets close to 2. Letter D, the last one here, says find f of 3. Or in other words, find the function value when x is equal to 3. So when x is right on 3, not just as I'm getting close to 3, but when I'm right on x equals 3, what is the value of this point? Well, there's a whole value. I mean, there's a hole there. So there is an undefined value for the function. At this point, the function is undefined. That's what a hole means, is that the function is undefined right there. So f of 3, the y value, when x is 3, does not exist. It's undefined. So you can write does not exist or none or something like that, because at x equals 3, the function is undefined. There is not an actual point there. There's a hole. So here are some of the types of end behavior questions you might see on your homework / on your test. As x goes to infinity, as x goes to negative infinity, as x goes to 3, and then finding a function value at a specific point. Okay. Now, we're going to talk about a couple different real-world examples of rational functions. So we're going to talk about some real-world problems that we might be able to solve using the tools that we've equipped ourselves with so far. So this example that we're going to go over in our guided notes, it says this: the concentration of a particular drug, the concentration C of a particular drug in a person's bloodstream, T hours after injection, is given by this formula. C of T equals 4T over 3 plus T squared. So this over here is the concentration. So this formula gives me the concentration of a particular drug in the person's bloodstream after a certain number of hours. So T represents the time in hours. So this formula, this rational equation, because this is a fraction, will give me the concentration of a drug in a person's bloodstream after a certain number of hours. Okay. So what is the concentration? This question asks, what is the concentration in the bloodstream after half an hour? So it says, what is the concentration after 0.5 hours. What is the concentration of the drug in this bloodstream after a half an hour? This is the kind of question the pharmaceutical and healthcare companies would need to answer. Well, if I put 0.5 or a half in for each of my t values, because t represents the time, I get 4 times 0.5 over 3 plus 0.5 squared. Well, 4 times 0.5 is 2. Let's see, I'm getting my handy dandy calculator. 0.5 squared is 3 plus 0.25. So I have 2 divided by 3.25. 3 plus 0.25 is 3.25. 2 divided by 3.25 is 0.615. It says round to 3 decimal places. The concentration of the drug in the bloodstream is 0.615. That concentration is typically measured in like grams per milliliter or something, but it's how much of the drug is in a certain unit of your blood. Because if the concentration gets too high of drug to blood, you're probably going to like die or pass out or something bad's going to happen. So they need to make sure the concentration in your blood is the right value. So in this case, after a half hour, the concentration of this drug in your bloodstream would be 0.615 grams per milliliter or something like that. So I just plug in the value of t and I solve. Okay. Letter B here says, at what time would you expect the concentration to be 1 milligram? Sorry, this should be milligrams, I guess, not grams. So at what time would you expect the concentration to be 1 milligram? So my concentration, I know. My concentration is 1 milligram. So I have 1 equals 4t over 3 plus t squared. Okay. Well, it says what time would you expect the concentration to be 1 milligram? So I'm going to need to solve for t. I'm going to need to solve for t. So I have 4t over 3 plus t squared equals 1. How would I go about solving this? There's a couple different things that right off the bat I can think of that I could go about solving this. So if I reflect back to when I talked about rational functions, I could write this side as 1 over 1. In order to solve this, I would need to have the same denominator, which means over here I would need 3 plus t squared. I need to multiply by 3 plus t squared on the bottom and 3 plus t squared on the top, which would mean I would have 3 plus t squared on the top and 3 plus t squared on the bottom equals 4t over 3 plus t squared. So that's one way I could go about setting up this equation, because then I could ignore the bottoms and just focus on the tops. 3 plus t squared equals 4t. Another way you could think about solving this problem is, since I have 4t divided by 3 plus t squared, I don't want anything in the denominator. So in order to simplify this, since I'm dividing by 3 plus t squared, I would multiply by 3 plus t squared on both sides. Because notice how 3 plus t squared divided by 3 plus t squared just cancels, and I'm left with 4t equals 1 times 3 plus t squared, which is just 3 plus t squared. Notice I get the same thing, so there's a couple different ways I could set up this equation. One other way I could do, I have 1 equals 4t over 3 plus t squared. If I write this as 1 over 1, some of you might remember the method of cross multiplying. So if I cross multiply here, 1 times 3 plus t squared is 3 plus t squared. And I write equals 1 times 4t is 4t. Look at that. I got the same thing in all 3 of those scenarios. So now I have 3 plus t squared equals 4t. So I need to solve for t, because I want to find what time I would expect the concentration to be 1 milligram. Okay, so I have 3 plus t squared equals 4t. Well, this is a t squared. This is a quadratic function, so I'm going to need to get everything on one side and set it equal to 0. So I'm going to go ahead and subtract 4t on both sides, which gives me 3 plus t squared minus 4t equals 0. I need this to be in standard form, so I'm going to go ahead and write it as t squared minus 4t plus 3 equals 0. And now, you guessed it, I'm going to solve this by factoring. If I couldn't solve it by factoring, I could also solve using the quadratic formula. Either way is fine by me. But in order to factor this, I'm going to multiply my first and my last terms, which gives me 3. And I need to find two numbers that multiply to make 3 and add up to negative 4. So what are two numbers that multiply to make 3 and add up to negative 4? Well, negative 3 times negative 1 is positive 3. Negative 3 plus negative 1 is negative 4. So my factors here would be x minus 3, t minus 3, and t minus 1. T minus 3 times t minus 1 equals 0. Which would, when I set each of those values equal to 0, I'm writing over here, t minus 3 equals 0 and t minus 1 equal to 0, I get times of 1 second or 3 seconds. Sorry, not seconds. Our time is in hours. I get 1 hour or 3 hours. So, check this out. The question was, at what time would you expect the concentration to be 1 milligram? So, after 1 hour, the concentration of this drug in my bloodstream is going to be 1 milligram. And then it seems like maybe it's going to go up and then come back down again, because at 3 hours, the drug is going to be at a concentration of 1 milligram again. So maybe on my graph, maybe it goes up, and at 1 hour, I have a concentration of 1 milligram. Then maybe it goes up and comes back down again, and by the time we're at 3 hours, it's kind of leveled down to be at 1 milligram again. Maybe we'll take a look at this graph in a minute and see if that's accurate. But at what time would you expect the concentration to be 1 milligram? At 1 hour and at 3 hours. There's two different times where the concentration would be at 1 milligram. Okay, last type of problem we're going to see with these real-world rational functions. So it says, what do you expect the concentration to be after several days? So what happens as time goes to infinity? So, on my graph, if I had the concentration as my y-axis and the time as my x-axis, we're trying to find as time gets really, really big, as time goes on and on and on and on, or as time goes to the right here, what's going to happen to the concentration of this drug? So, I'm going to be looking for a horizontal asymptote. I'm going to be looking for my horizontal asymptote, because as I go on and on and on and on, my graph is probably going to get pretty close to this end right over here. So if you remember how to find a horizontal asymptote, if I look at the largest exponent in the top and the largest exponent in the bottom, I have one up here, two up here. When the largest exponent in the top is smaller than the largest exponent in the bottom, my horizontal asymptote is y equals 0. So my horizontal asymptote, let me change colors here. My horizontal asymptote is going to be this line right here. So, as time goes on, as time goes forever this direction, what is my graph going to be doing? It's probably going to be getting really close to, but never actually touching, 0. So what would I expect the concentration to be after several days? Well, the concentration in the blood as time goes on is going to get really close to 0. Okay, with all these questions, I'm going to hurry and pull up my Desmos graph, and we're going to graph this. Make sure we're not crazy. So my graph, I have C of t equals 4t over 3 plus t squared. So this is kind of an interesting rational function. This is a unique rational function that we've never really seen before. But notice here, my function goes up a little bit and then comes back down. Notice right here at 1, when time was at 1 hour, the concentration of the drug in the blood was 1. That's what we found earlier. At 3 hours, the concentration in my of the drug in my blood was, again, at 1 milligram, so that makes sense. And as time goes on, as I keep going to the right forever and ever and ever, notice that the concentration of the drug in my blood is going to get really, really, really close to 0. This x-axis, it's going to get really, really close to 0. So, if I come back into here, so what do I expect the concentration to be after several days? What happens as time goes on? So as time goes on, the concentration in the blood is going to get really close to 0, which is hopefully, I don't want that drug to be in my bloodstream forever. I want it to eventually basically go away, so the concentration of the drug in my blood is going to get really close to 0. And I also confirmed this right here. I looked on my graph and determined, yeah, at 1 hour and 3 hours, the concentration was going to be at 1 milligram. At a half hour, if we pull up the graph again, at about a half hour, so like at about here, at 0.5, when the time is 0.5, the concentration was about 0.615, which again is what I would have expected here. So those are some of the real-world situations we can find ourselves in with applying rational functions. So by the end of this lesson, these are the things that I want you to be able to do. I want you to identify the end behavior of a rational function. Where is the function going as x gets big, or as x gets small, or as x gets close to a particular number? Identifying the function's behavior at an asymptote, and solving real-world problems with rational functions. I hope that was helpful. Please reach out to me if you have any questions about these real-world problems we can model with rational functions. I hope that you enjoyed that as much as I did.